Hello guys, this is our first problem solved for Bryton cycles. I apologize because we have something going on here in the classroom near to where I am recording, so you will see here some steps. Well, we have a simple Bryton cycle using air as a working fluid with a pressure ratio of 10. The minimum and maximum temperatures in the cycle are 295 and 1240 Kelvin, assuming an isentropic efficiency of 83% for the compressor and 87% for the turbine. Determine the air temperature at the turbine exit, the network output, and the thermal efficiency. So we're gonna start by drawing what is our diagram. So we have a compressor, and then we have the combustor, then we have the turbine. As we discussed, part of the work is used to move the compressor. The rest of the work is our network. We close the system. We are going to analyze it as an air standard cycle with some heat exchanger that goes from the exit of the turbine to the artificial condenser. We don't have a condenser, we take it to the atmosphere actually. So we have our state 1, 2, 3, and 4. If we do it on a PV diagram, this will be something similar to this. If we do it on a PV, if we draw it on a PV diagram, it will be something similar to this. We have a constant pressure, we have an expansion, constant pressure heat addition, compression, constant pressure heat addition, and constant pressure heat rejection. We don't know the pressures, but we know pressure ratio, which is P2 over P1 is 10. If we look at a TS diagram, we have our isentropic compression, constant pressure heat addition, isentropic expansion, constant pressure heat rejection, and we know 295 until 40. We also know the isentropic efficiency of the compressor is 0.83, and the isentropic efficiency of the turbine is 0.87. We are asked to find the temperature of the air at the exit of the turbine, so that will be T4, the network, and the thermal efficiency of the cycle. We're not being told what to use, so we're going to use variable specific heats. That means table A17. Okay, so we can start by saying that our efficiency will be network divided by Q in. We can expand this network as work of the turbine minus work of the compressor divided by Q in. Work of the turbine, and this is the ideal one. Since we have an isentropic efficiency, this will be 2s. We're going to have a 2 actual. Let me draw this a little bit better. I don't know why I can erase. So this will be 4s. And I will have a for actual. So work of my turbine will be H3 minus H4 actual, and work of my compressor will be H2 actual minus H1. Q in will be H3 minus H2 actual. All this tree comes from first law analysis for open systems. Okay, we discussed that in our previous material. So since we know the temperature of these two, we can easily compute states 1 and 3, and we notice then that we have these two values, but we are missing the 4a and 2a. So in order to find it, we're going to use our usual relations of efficiency of the compressor to be H2s minus H1, H2 actual minus H1, and the efficiency of the turbine to be H3 minus H4 actual, H3 minus H4s. H2s and H4s, we can find it from isentropic relations if we were having constant specific heats, but we're going to get it using table A17. So state 1 we know temperature is 295. With this value we can get H1 to be 295.17, and the reduced pressure will be 1.368. How do we get this number? We get it from our table A17 using this row. Similarly, we can get state 2 state 3, and we know temperature is 1240 Kelvin. So H3 equals and reduced pressure is a dimensional. So how do we get state 2s? So how do we get state 2s? Well, we know PR2 divided by PR1 equals P2 divided by P1. So solving for PR2 will be PR1, which is 1.3068 times P2 over P1, which we don't know, but we know the pressure ratio, which is P1 over P2. So sorry, the pressure ratio is P2 over P1. So it will be times 10. PR2 will be 13.068. So we need to look into our table and look in this column for the value of 13.068. And as we go down, we notice that we have 13.5 for 570 and 14.38 for 580. So by interpolation, we have H2S to be 570.23 kilojoules per kilogram. We do similarly to state 4. For S, we'll have PR4 divided by PR3 equals P4 over P3. PR4 will be 27.23. This number divided by 10. So we need to look for this value, and we notice that is in between these two numbers. So again, by interpolation, we have H4S to be 702.07. We're not getting temperature with this interpolation because this is the 4S, and we were asked for the final temperature at the end of the exit of the turbine, but it's the actual temperature, not the isentropic temperature. So if we substitute we have that H2R to be H2S minus H1 divided by compressor efficiency plus enthalpy 1. So this will be, just by substitution, we'll have 626.69 and H4R will be H3 minus the efficiency of the turbine times H3 minus H4S. Notice that I have called R here, which is the same. We are gonna change it back to actual instead of R. So we have coefficients, and again substituting the values that we have, H4 actual will be 783.04 kilojoules per kilogram. Now if I go to my table A17 and look for that value, 783, I will notice that is in between these two values. So by interpolation, T4 actual is equal to 765.25 Kelvin. And this is our first result. Now, to compute network, we just need to substitute and the work of the turbine will be 1324.93 minus 783.04. This is 541.89 minus the work of the compressor, which is 626.69 minus 295.17 is equal to 331.52. So if we make the difference, we have our network to be 2010.37. If we divide this by Q in, and Q in is equal to 1,324.93 minus 626.69. This is equal to 698.24. So we make this division, we will have 0.3013. So these are our two values network will be 210.37 kilojoules per kilogram, while the thermal efficiency is 30.13%. And these are the two values that okay. With this we finish this example. Please see our next video for solutions. Thank you.